Hello everyone, welcome back to Z Physics. What we're going to be doing today is solving the 2019 Unified Physics paper from OCR. Just before we get started with the questions, just a little disclaimer that this video is not affiliated with the exam board and these are not official solutions. So if you're after the official paper with the official solutions and the examiner's reports and some very useful information, please head to the OCR website and you can see the link in the description for that. Okay, well, let's have a look at question 1, which is all about a rocket. Really interesting. Okay, so we have a toy rocket which is made from a 1.5 liter plastic bottle, and we have some fins for stability. Really cool. Now, initially it contains 0.3 liters of water, and that leaves 1.2 liters of trapped air at a temperature of 70 degrees. A pump is used to increase the pressure within the plastic bottle to 2.4 times 10 to the power of 5 pascals at the start of liftoff. And we have a diagram of this cool contraption over here. For part A, we need to calculate in moles the amount of trapped air in the bottle at the start of liftoff. Okay, well, now for this, what we're going to be using is essentially the PV is equal to nRT equation. So PV is equal to nRT. Because we're looking for the amount of moles, I'm just going to be rearranging this for N, and we can see that N is going to equal to PV divided by the gas constant R times the temperature. Just a little note, very typical mistake, T here is in Kelvin. Really important to consider. Okay, well, let's plug in some values. So first off, the pressure just before the moment of liftoff is 2.4 times 10 to the power of 5. Okay, so let's just write that down. 2.4 times 10 to the power of 5, and we have 1.2 liters of trapped air, so this will actually equal 1.2 times 10 to the power of minus 3, because we have this conversion factor that we are given here in this question. So this is going to be times 1.2 multiplied by 10 to the power of minus 3, and now let's divide by the gas constant, which is just 8.31, multiplied by the temperature, and let's see what the temperature is. So it's given to be 70 degrees, so we need to add 273, which is going to give us 300 Kelvin. Now when we put that into a calculator and we get that to a decimal, we're going to use up to 2 significant figures. So this is going to be 0.12 moles of air. So part B, the trapped air pushes the water downwards, causing the rocket to rise. The temperature remains constant, and we want to calculate the final pressure of the trapped air just before all the water has been released. Now, the very statement that the temperature of the air remains constant is a clue for us to use Boyle's law to calculate the final pressure. You don't need to write the explanation of why you're using Boyle's law in the exam. However, in this video, I would really like to not only just solve the problems, but explain how I'm actually thinking about what equation to use. Now, if the temperature remains constant, in the equation PV is equal to nRT, the amount of substance also remains constant, then this whole right hand side of the equation will be a constant, which means that PV will be equal to a constant. Pressure times the volume will be a constant. This would of course mean that P1 V1 will be equal to P2 V2. We can just rearrange this for the final pressure, P2, which is going to be equal to the initial pressure times the initial volume. Then we're going to divide that by the final volume. Okay, well, let's have a look at what those values are actually going to be. So P1 is just our initial pressure before the water is pushed downwards, and this was given in the question just over here. So that's just 2.4 times 10 to the power of 5 pascals. So let's just write that down. And this is going to be 2.4 times 10 to the power of 5. Now let's multiply that by the initial volume. Before the water is pushed out, our initial volume is just this volume here, which is given to be 1.2 liters. Well, that's equal to 1.2 times 10 to the power of minus 3 cubic meters, and we're going to write this down. So this will be times 1.2 times 10 to the power of minus 3. Now our final volume, and this is really important, will actually be the entire volume of the whole bottle, of the whole sort of model rocket. And we're given initially in the question that the final volume is 1.5 liters. So let's just write that down, 1.5 times 10 to the power of minus 3. So let's put all these values into a calculator, and we are going to get about 192 and then 3 zeros after that. So we can write that as 1.9 times 10 to the 5 pascals. The next question is really interesting. We have quite a lot of data on this rocket. So we have the mass, we have the cross-sectional area, we have the initial pressure, the atmospheric pressure, etc. We need to use the data to show that the upwards force, and this has been written in bold. The reason for that is we're not interested in the resultant force, we're interested in just the upwards force. So this here is our rocket, and there's going to be some upwards force, also going to be some weight. We're only interested in the upwards force. What is that force actually caused by? When the rocket is essentially going up, it will be caused by differences in pressure. Because our pressure is defined by force over area, the force that's created in this case will actually be caused by the differences in pressure. So let's call that delta P, and that difference in pressure before and after will be responsible for that force. So let's just rearrange for the force. The force will be delta P multiplied by A, which means that the force will be equal to the difference in pressure. Now our final pressure we've actually calculated is 2.4 times 10 to the power of 5. Take away the initial pressure, which will be the atmospheric pressure. So really tricky question actually. So 1.0 times 10 to the power of 5, and let's multiply that by our cross-sectional area, which is given up here. That's going to be 1.1 times 10 to the power of 4. Plug that into a calculator. We're going to get about 15.4 newtons. Well, also in this case we're only working up to two significant figures, so let's just say that this is equal to 15 newtons. Okay, next one. Hence, calculate the initial vertical acceleration of the rocket. Well, now we will need to know the mass of this rocket water system. The reason for that is because we're going to, in order to find the initial acceleration, we're also going to need the weight. So imagine this rocket is this dot over here. It's going to have some force acting on it, and then we'll also have some weight. And what we're going to do is we're going to take them away. We're going to set the result equal to ma, and we're going to find the acceleration from the resultant force. Now let's calculate the weight though. So for that we're going to need a few numbers that will be equal to the so the mass of the bottle plus the mass of the fluid times 9.81. Should we just do that in two separate steps? So let's just keep it simple. I'm going to calculate the mass first of all. Okay, well, let's have a look at some values. The mass of the empty bottle is about 0.05 kg. Okay, so the mass is 0.050 plus, let's add the mass of the water. Okay, so where is it? Okay, so it contains 0.3 liters of water. A useful rule of thumb to remember is that 1 liter weighs 1 kg. So 1 liter of water in specifically, so 1 liter of water weighs 1 kg. So 0.3 liters of water is going to weigh 0.3 kilograms. Okay, so let's just add that in, leaving us with a combined mass of the water plus the toy rocket of, so that'll be 0.3, which will be equal to 0.35 kilograms. Okay, now that we have the mass, we are ready to find our resultant force and set that equal to MA. So our resultant force, let's just write that F, let's call it F net, will be equal to mass times acceleration. The upward force is just this force here, which we've already calculated, and then from that we're going to need to take away the weight. So in the previous question we found the upward force to be about 15 newtons. So in fact this force F is actually equal to 15 newtons. So it'll be 15, take away the weight, don't confuse that with the mass, so that's going to be 0.35, because the weight is equal to mg. We've already found our m, and all we need to do is just multiply that by g, so times 9.81, and this will be equal to the mass times the acceleration of the system, so it's going to be 0.35 times the acceleration. Please keep in mind that this will only be the initial vertical acceleration, because as soon as the rocket starts accelerating, the mass will actually be changing. So this is just the initial vertical acceleration. Okay, well, let's just rearrange for the acceleration, and I quite like rearranging first and only then putting values into the calculator. So A will be 15, take away 0.35 times 9.81. We're going to divide that by 0.35, and putting that into a calculator, we are going to get 34.19 meters per second squared. Let's leave that up to 2 sig figs as 34 meters per second squared. And the last part of this question discuss whether adding more water initially would enable the rocket to reach a greater height. This is actually a really tricky and interesting question. The way to tackle these questions is to start off with what you definitely know is true, the very basics, the very fundamentals. If we had more water initially, the initial weight of the rocket will for sure be greater. So we can just write that down, that the initial weight will be larger. If the initial weight is larger, so let's say that this factor here increases in the previous question, then the acceleration will surely decrease because they're inversely proportional. So we can say that at least initially, the initial acceleration will decrease. However, there is one critical thing which we need to consider as well, and that is that the time the rocket will be working for will actually be increasing as well. I mean, if you imagine that, let me just get rid of my drawings from the previous question, but the amount of time that the water will be going out and thus providing a force will be increasing, because if the water was filled up to this level, it would take longer for the water to be expelled, and this is actually our fuel for the rocket. So this is a very, very interesting, tricky question that we cannot fully answer, but we can analyze. So what we can say is that the time for the water to be expelled will increase. The height depends on all of the above factors, so in a way it's actually impossible to give a absolutely accurate answer on this, but this question wants us to analyze the factors between them. So question number 2, this is a radioactivity question, and okay, so we have 6027 cobalt is produced by irradiating the stable isotope cobalt 59 with neutrons, and each nucleus then decays into a nucleus of nickel by the emission of a low energy beta minus particles. This is essentially beta decay, beta minus decay. 1 outer particles and 2 gamma photons. Complete the nuclear equations for these processes. Okay, well, so first off we have a neutron interaction, and remember up here we have the number of protons plus neutrons, and down here we just have our proton number, which is in this case 27 here. So there's no protons inside our neutron, surprise surprise, so this here was going to be 0, and and we're going to have a number 1 on top, obviously because it's just 1 neutron. Okay, well, after we reach this stage, this is the second stage of our nuclear decay, which is beta minus decay. The beta minus decay is going to emit an electron, which will have -1 here, 0 on top. In beta minus decay, we have gained a proton, so a neutron turns into a proton, so this here will be 28, but the total number of neutrons plus protons remains constant, so this here will be 60, and we also have an anti-neutrino, which is given the symbol here with a little bar on top to showcase the fact that it's an anti-neutrino. A useful tip to remember what it's an anti-neutrino: if you see a minus here, if you see a little horizontal bar here, then you need a little horizontal bar up here as well. Okay, part B, students want to carry out an investigation into gamma photon absorption using a source of cobalt 60. They add sheets of lead between the source and the radiation detector, and we're keeping those in fixed positions. The cobalt source emits beta radiation as well as gamma radiation. Explain why this would not affect the experiment. Well, the gamma rays, or a significant portion of the gamma rays, are going to pass through the lead, whereas the beta radiation will be absorbed by the sheets of lead. So we can just write this down, that beta radiation will be absorbed by the lead. Okay, next one. Okay, part II, or part 2, the students record the number n of the gamma photons detected in 10 minutes. We have a little table of results here with n, d, the distance in millimeter, and then we also have the natural log ln of n. N and d are related by the following equation. This is just our exponential decay equation, where n0 and mu are constants. The student decided to plot a graph of n against d. Show that this gives a straight line with the following gradient and the following y-intercept. Okay, well, let's do this, first off, I'm going to write down the equation. N is equal to n naught e to the minus mu d. Okay, well, let's rearrange for the exponential. This is our first step, so it's going to be n over n naught e to the minus mu d. Let's take the natural log of both sides. So ln of n over n naught will be equal to ln of e to the minus mu d. And remember, ln and the exponentials will sort of, their inverse function, so they undo each other. And what we're going to get is that ln of n over n naught will be equal to minus mu d. Just write that more clearly. So minus mu times d. Because of the properties of log, the natural log of n over n naught is equal to ln of n, take away ln of n naught, which is equal to minus mu d, which means that the natural log of n will be equal to this expression here. And now we can directly compare this with y equals mx plus c minus ln of n naught, and like so. Click and just write y is equal to mx plus c here, and we can see that if ln is on the y-axis, if d is on the x-axis, we have our gradient to be minus mu, and we have our intercept to be that. Just to be super clear, I'm going to write down that the gradient is equal to minus this constant, and our intercept c is equal to the natural log of the initial number. Okay, complete the missing value of delta n in the table, include the absolute uncertainty. Show your calculation of the absolute uncertainty in the space below. Well, this was actually a really tricky question in terms of the absolute uncertainty. First off, let's just calculate the ln of 300, which is just 5.70. So I'm writing this, I'm doing a quick check. We need to conserve decimal places in tables. So here we're given 2 decimal places, 3 significant figures, and I'm keeping consistent with that. The absolute uncertainty is tricky. We've not dealt with officially in this course with calculating the absolute uncertainties within logarithms or ln's. So what I'm going to do is I'm going to use the rule that my absolute uncertainty is equal, so absolute uncertainty is equal to half the range. Okay, now because my value of n could be anywhere between, because it's 300 plus or minus 40, it could be anywhere within 340, or at the lower end we're going to have 300 minus 40, which is 260. So our range is actually going to be between those two values, between the natural log of those two values, like so. Okay, well, let's show our calculations. So let me just write that the absolute uncertainty, I'm just going to call that AU in this case, is approximately equal to half the range. Okay, good rule of thumb to remember. So this would mean that our absolute uncertainty, ln of 340, is at the top of our range. Let's take away the natural log of 260. Then we're going to divide by 2, and this will be approximately equal to 0.13 up to 2 significant figures. So we can write this down here as plus or minus 0.13. Now, coming up next, we have a graphical question, and in this figure we need to plot the missing data point. So I've plotted this quite carefully right over here. Keep in mind that we're going from 5.5 to 6, so each little square is going to be 0.05, and then I've drawn the line of best fit in black over here, and I've also drawn the line of worst fit in red. Remember, in order to draw the line of worst fit, it's bottom of bottom to top of top, it's either the steepest or the shallowest line that we can draw on our graph. Okay, well, for the next question, what we needed to do is to determine the value of our constant, including our absolute uncertainty. So in order to do so, our value of the constant can be determined using the gradient of the line of best fit. And I've got my gradient calculation here. We're going from 5.7 we're going from 8.3, sorry, to 5.7, and we're taking away the values using the fact that the gradient is change in y divided by change in the x-axis, which gives us about 52 m to the power of minus 1. Now, in order to determine the absolute uncertainty, we need to find the gradient of the line of worst fit. So let me just do that. I'm going to write m worst fit like so, and we can see that they differ a little bit. So we're going from 8.5 to about 5.6. Okay, well, our gradient of the line of worst fit will be equal to 5.6, which is our final y. Take away the initial y, which was 8.5. I'm going to divide that by essentially the same number. So we're going from 0 to 50. So it's going to be 50 times 10 to the power of minus 3. Putting that into a calculator, we're going to get minus 58 m to the power of minus 1 for the gradient of the line of worst fit. Now, our original gradient for the line of best fit, I'll just write that here, was minus 52. So you might remember the formula that I've given you, that our percentage uncertainty in the gradient is equal to the line of worst fit, take away the line of best fit, divided by the line of best fit times 100. Well, our absolute uncertainty, I'll just write that AU in the gradient, is just simply the two values taken away from one another. So in this case, our absolute uncertainty in the gradient will be simply equal to the gradient of the line of best fit, take away the gradient of the line of worst fit. So it's going to be minus 52 minus minus, so it's going to give us plus 58, which is just going to give us 6 m to the power of minus 1 as our absolute uncertainty. Okay, final question. Determine the thickness d half of lead, which halves the number of gamma photons reaching T. Okay, well, remember our equation is that n is equal to n naught e to the minus mu times d. So what we really want to do is we want to halve the number of photons. So n over n naught will be equal to e to the minus mu d. We've already done that, but n over n naught in this case will be equal to half if we are halving the number of gamma photons. So in this case, we can simply say that this here will be equal to half, and this will be equal to e to the minus mu d. Now let's start taking some logs. So what I'm going to do is ln of a half, like so, is equal to minus mu d. Let's flip the logarithm. So I'm going to get ln of 2 is equal to mu multiplied by d, which means that our distance d will be equal to ln of 2 divided by mu, which we've already found in the previous question to be 52. So we're going to use this answer here that I'm underlining. So it's going to be ln of 2 divided by 52, which is about, let's see, 0.013 meters. Okay, question 3. We have figure 3.1 showing the design of a mechanical torch. It's a really interesting design. So we have this magnet, and anytime we invert the torch, the magnet is essentially going through this ring, and when that happens, there is a change in the magnetic flux linkage, which actually produces an EMF. And that's how the torch works. And we also have a little figure over here which shows the variation with time of the induced EMF as the magnet falls with a distance h. Explain the shape of the curve above. Okay, well, there are a few features that we'll need to explain. First off, we have a couple of points at which the induced EMF is 0. So at the start, just before the magnet starts, it's naturally 0 there. But there's also another point at which the EMF is 0, and this is right over here. Now this will be happening when the magnet is going right through the actual ring. Because the magnet is actually accelerating because it's going down because of gravity, the induced EMF in this second region over here will be greater. And this is simply because the magnet is moving faster in this region over here compared to the one above. Okay, well, let's put all that we've said this into words. So it's a 3-marker question to explain the shape of the curve. Remember, explain in exam language means tell me what is actually causing this. Okay, so our first bit of explanation is that induced EMF is caused by the change in magnetic flux linkage This is essentially due to Faraday's law, which says that the induced EMF is proportional to the rate of change of magnetic flux linkage. For those of you guys that don't remember the law, it says that our induced EMF, let's call that E, is equal to the rate of change of magnetic flux linkage, like so. Okay, well, now our next bit of explanation would be to try and explain why is this first peak positive and why is this second peak negative. Well, because when the magnet is approaching initially, let's say that it's approaching, I don't know, let's say it's approaching north to south like this. And as it is going through, the magnetic flux density will also be changing sign like so. So the ring will first off see the North Pole, then it's going to see the South Pole. So what we can say is that the EMF changes sign, and that will be because the magnetic flux density changes sign as the magnet falls. I'm also going to say that the induced EMF is greater at the second peak because the magnet has accelerated. Okay, next one. Okay, part B is a calculation question. When the torch is inverted, the pulses of the EMF in the figure cause a capacitor, and we're given the capacitance to become charged. So each positive and negative pulse adds this much charge, 9 millicoulombs, to the charge stored in the capacitor. The torch is inverted 80 times. Okay, so with each inversion, we're going to get twice that amount of charge. Calculate the total energy stored in the capacitor. Okay, well, we know that the energy is equal to a half CV squared. We don't really know the voltage. However, we do know that Q is equal to CV, which means that V is equal to Q over C. Okay, well, let's substitute that in. So it's going to be equal to a half C. Now, rather than V, I'm going to write Q over C squared, which is equal to a half C times Q squared divided by C squared, which is equal to a half Q squared divided by C. Okay, now the charge in this case is going to be a half times. So that will be 2, because each positive and each negative pulse will add that amount. So 2 times 9.0 times 10 to the power of minus 3. They're going to multiply that by 80, and I'm going to divide this by, that will be squared, by the way, and I'm going to be divided by the capacitance, which is 0.12 farads. Put all of that into a calculator, and we are going to get 8.64, because we're working up to 2 significant figures. Let's leave that as 8.6 joules. Okay, the next part, when the torch is switched on, the energy stored in the capacitor lights a 50 milliwatt LED. Estimate the time for which the LED lights. Okay, well, let's write down some equations. We know that power is equal to energy per unit time. We've just calculated the total energy. So what I'm going to do is just rearrange for the time, because we're given the power already. So the time will be equal to the energy divided by the power. So it's going to be 8.6 watts and 8.6 joules, excuse me, divided by 50. Let's not forget the prefix, times 10 to the power of minus 3, which is equal to 172. Up to 2 significant figures. Let's write that down as 170 seconds. Okay, part C, the extended response question to 6 marker. In the torch, the gravitational potential energy of the magnet is converted into electrical energy supplied to the 50 milliwatt LED. You are asked to investigate whether the efficiency of this energy conversion depends on the number of inversions of the torch. Okay, so first off, we need to describe how we're going to make accurate measurements. I'm just going to underline that, collect our data. I'm going to explain how we're going to use the data that we've collected in this experiment to reach a conclusion. Okay, well, the idea is that we have some gravitational potential energy that's being converted to electrical energy, and the electrical energy is just given by the power multiplied by the time. Now, with every number of inversion, or with every inversion, we're getting another factor of gravitational potential energy. So I'm going to say that I'm going to add a little constant multiplying the gravitational potential energy. For instance, if I had 1 inversion, I'm just going to have mgh. If I had 2 inversions, I'll have 2 mgh. If I have n inversions, I'm going to have n mgh. Well, let's think about what we're going to need to measure. We know that G is 9.81. We can count the number of inversions in our experiment. We can measure M with a top and balance. We're going to need to work out the height quite carefully, because if we look at our diagram in this question over here, that really doesn't take into account the size of our magnet. Well, let's have a look at my answer to this question. So for our input energy, what I've written down is to record the number of inversions n. We're going to measure the mass of the magnet with a top hand balance. We're going to measure the tube length and the magnet length with a ruler. Then we're going to take them away from one another. We're going to calculate the height to which the magnet has dropped. Afterwards, we're going to simply calculate the input energy using NMGH. And this is how we are going to find our input energy. Our next step would be to calculate the output energy. The way we're going to do that is we're going to switch the torch on and we're going to measure the time until the LED goes off. And we're going to measure the time, we're going to call that time T, and we're going to measure that with a stop clock. Afterwards, we're going to calculate the output energy just simply by using power multiplied by time, where T is the time that we've measured. Remember, we're actually given the power of the LED, which is 50 milliwatts, so it's going to be 50 times 10 to the power minus 3 multiplied by that time. We're going to calculate the efficiency by the energy output, the output energy divided by the input energy multiplied by 100. One thing that I'm going to add here is that we should perform this experiment in a dark room, so I would just say to perform the time measurement in a dark room. This is really helping us to get some accurate readings. Okay, now our next thing that we need to do is to explain how we're going to use data to reach a conclusion. So far we've got examples of how to find the input energy, MGH, and how to find the output energy, which is found by power multiplied by time. The idea here is that after we find our efficiency, what we should really do is to repeat this experiment. So let's say that we're going to repeat the experiment for different values of n. Calculating the efficiency each time. In order to really understand the relationship between them, what we should really do would be, in order to reach a conclusion, we would need to plot a graph. And this would be a graph on our number of inversions against our efficiency. For instance, if the graph is let's say a straight line through the origin, that would mean that they're directly proportional. It could be another relationship, so on and so forth. Okay, so let's just write this down, and I'm just going to remove this. Okay, so let's write this down. Plot a graph of n, the number of inversions, against the efficiency. After we've done that, we could compare the efficiency directly for different values of n. So let's just write this down. So I'll just say to compare the efficiency for different values of n, for different values of n. Now, as always with 6 markers, I'm just going to go back and I'm going to check whether I've done everything. So describe how to make accurate measurements. So we've talked about accuracy, we've talked about taking readings with a stop clock, with a top band balance, with a ruler, and we've also going to take some readings in a dark room, and we have all of our measurements to collect our data. and we've also explained how we're going to use the data to reach a conclusion. So I'm reasonably happy with the 6-marker question, and let's move on to the next one. Okay, question 4. We have an airport with a conveyor belt, and we're given that we have a suitcase of mass 8 kilograms that is moving at a constant speed of 1.5 meters per second. And we have a free body diagram of the suitcase with R and F and W going down. Looking at this problem, I can almost instantly see that it will be about the resolving the forces. And as it says over here, by using a vector triangle or by resolving forces, calculate the magnitude of the forces F and R. I personally prefer doing this with resolving forces, but if you get the same answer using a vector triangle, by all means go for it. Okay, well, let's think about those forces. Now, the weight can always be represented on an inclined plane as having components which are both parallel and perpendicular to the slope. So we can think of this weight force as having a component which is going to push our suitcase down the slope, so that would be parallel, like so, and it will also have a perpendicular component which will be pushing it vertically down as well, or at 90 degrees, sorry, just like that, just as shown. Now, if our suitcase is in balance, this component will be equal to R, and this component here will be equal to F. Now let's think a little bit about angles. This angle here is 30. If we're to extend this one, because this one here is 90 because the weight is perpendicular, we're going to see that the angle up here has to be equal to 60 degrees, which would mean that this angle here will be equal to 30 degrees. Okay, well, let's have a look at our components. If we have essentially this here is W, which is our hypotenuse. This here is a right angle, by the way. So the two components, this one here will be W, so that's the perpendicular component. That's the adjacent, so it's going to be W cos 30. Let's write this a little bit smaller so that we can actually fit this. So, what have we done here? So let's try again. So that's just W cos 30. I'm going to write it like that. And the component up here, because that's the opposite to a sine angle, will be W sine of 30. So that's just this component over here. W cos 30 is this one. Okay, well, let's do the calculation now. So F will be should be equal to the W sine 30 if the whole system is in balance, and R should be equal to W cos 30. So let's start off with R. So R will have to be equal to the weight multiplied by the cosine of 30. So the mass was 8 kilograms. So the weight is equal to mg cos 30. So it's going to be 8.0 times 9.81 multiplied by the cosine of 30. And this is going to give me 67.9. So let's write that. It's 68 newtons. Okay, now that we have the normal reaction, let's figure out the frictional force. So F will just be the other component, so it's going to be W sine of 30, which is going to equal to mg times the sine of 30. That's going to be 8.0 times 9.81. multiplied by essentially a half, which is the sine of 30. Putting that into a calculator, we get 39.24, which we're going to leave as 39 newtons up to two significant figures. So let's get this right. F is 39 and R is 68 newtons. Okay, next one, we have the center of mass of the suitcase is now moving at 1.5 meters per second along a semicircular arc of radius 2 meters. Calculate the magnitude of the centripetal force acting on the suitcase. Okay, well, we're going to just use F is equal to mv squared over r. So what we're going to use is that the mass is 8.0, our speed is 1.5 squared, then we're going to divide by the radius, which is 2.0. Into the calculator it goes, and we get 9.0 newtons for our centripetal force. Okay, next part, when the suitcase is at line YY, the magnitude of the force is larger, or the magnitude of the force F is larger, and the magnitude of R is smaller than the other line, XX. Explain why this is so. Okay, well, you have this line over here compared to the previous line over here. So why is that the case? When the suitcase actually starts turning, then there now has to be a centripetal force acting, and that centripetal force will be acting towards the center of rotation. Well, that will now be our resultant force. And that centripetal force can only be provided by an increase in the frictional force. So it's a component of the frictional force that is actually causing this to turn. Now, an increased frictional force will mean a higher vertical component of F. Let me just explain that. So let's say that in this configuration, F is going to have this much of a vertical component, and this vertical component will be balancing out some of the weight. However, if the frictional force suddenly increased this much, then I'm going to have this much of a component balancing out the weight. Now, if that's the case, the normal reaction is going to be smaller. So in other words, as F increases, R will have to decrease. So increased F means a higher vertical component of the force, of the frictional force. Let's just add balancing the weight. Therefore, R must decrease. Okay, question 5. Now, this question only looks a little bit intimidating because there is quite a lot of information that is given. But if you really think about it, this is actually just a standard diffraction question. We can just use our equation that d sine theta is equal to n lambda. Please be aware that even though this is kind of a waves equation about diffraction, the equation is actually given as in the formula booklet as part of module 5. So this is because we use that equation quite extensively to analyze stars, and we do stars in module 5. Okay, well, we're given the following information. So we have some incident light from the slit, and we're given that this distance here is 0.5 meters. This one here is 15 centimeters. So we could really easily calculate our angle of diffraction. Even before I read the question, I could just quickly say that theta will be equal to the inverse tangent of 15 centimeters, which is 0.15 meters, divided by 0.50 meters. So we have an idea over here where this distance x is, and we have some measurements over here for what the distance x is for violet, blue, green, and red. The students decides to determine the wavelength of the photons which form the red line. Okay, so for the red line, the distance x is actually 10 centimeters. So this one here is 10 centimeters. So our calculation for the angle will actually be equal to 0.0 divided by 0.5. Okay, well, what we're being asked to do is to describe how the information that has been given can be used to determine the wavelength. That's one thing. Then finally, we want to estimate the percentage uncertainty. Okay, well, first off, for our wavelength calculation. As I said, we're going to use the equation that d sine theta is equal to n lambda. In this case, this is the first order of diffraction, so n is equal to 1. We're going to find d using our standard procedure. D is equal to 1 over the number of lines per millimeter, so that's going to be 300, and because if there are 300 lines per millimeter, the number of lines per meter, in order to find that, we're going to need to multiply by 1,000, so 300 times 10 to the power of 3, which is going to give us 3.3 times 10 to the power of minus 6. We're going to find theta using the equation that tan theta will be equal to 10 over 50, therefore theta will be the inverse tangent of 10 over 50, which is 11.3 degrees. Afterwards, we could really easily calculate our lambda. Lambda will be equal to d sine theta, which is 3.3 times 10 to the power minus 6 multiplied by the sine of 11.3 degrees, and if we do that successfully, we're going to get about 6.5 times 10 to the power minus 7 meters, which is about 650 nanometers. So we know that we're within the right range of values for red photons. In terms of the uncertainty, well, let's have a look at the equation. The equation is that d sine theta is equal to n lambda. Now, d and n were just given in the question with no uncertainty assigned to them, so we can just say that they have negligible uncertainties. Now, for the uncertainty in lambda, we do find that by performing a calculation, because we found our angle using the formula that will be equal to the inverse tangent of these two distances. We need to figure out our percentage uncertainty in one, and then we're going to add the percentage uncertainty of the other. Why am I adding percentage uncertainties? Because I'm dividing the quantities, and if I'm dividing the quantities, I need to add the percentage uncertainties. Now, the percentage uncertainty in each case is going to be 0.1 centimeter. So what I've done is I've assumed that my absolute uncertainty is 1 millimeter. So maybe I'm just going to write this over here on the side. Once again, this will probably not add to you guys scoring any marks, but it will help you with your understanding. So what I've done in my solution is that I've assumed that my absolute uncertainty, which I'm calling it AU, is plus or minus 1 millimeter. Now, you would have scored full marks if you'd chosen half a millimeter as well, which is equal to 0.1 centimeters. And what I've done over here is I've just simply found the percentage uncertainty in one of the distances. Let's call that in the measurement of x, plus the percentage uncertainty in the other distance. Let's call that, I say in the distance x is equal to 10 centimeters, and the percentage certainty in 50 centimeters, which is just this length over here. And remember, our percentage uncertainty in each is plus or minus the absolute uncertainty, so that's plus or minus 0.1 divided by a value 10 plus plus or minus 0.1 divided by our value 50, which gives us 1.2%. So this is where this value comes from if you are not completely sure. Because we've calculated lambda simply by multiplying d by sine theta, then and because n is equal to 1, we're kind of ignoring that, then our percentage uncertainty in sine of theta will be equal to this percentage uncertainty, which will be equal to the percentage uncertainty in the wavelength. So this will be 1.2%. Okay, the next one, this one here is not so bad. Show that the energy of a photon of wavelength 486 nanometers is 4.09 times 10 to the power minus 19, while the energy of a photon is simply given by hc over lambda. So h is 6.64 times 10 to the power of minus 34 multiplied by the speed of light, which is 3.0 multiplied by 10 to the 8. And let's divide that by our wavelength, which is 486 times 10 to the power of minus 9. And putting that into a calculator, we're going to get our answer of 4.09 times 10 to the power of minus 19 joules. Okay, next one, figure 5.4 shows some of the energy levels of an electron in a hydrogen atom. Draw an arrow to show an electron transition which would cause the emission of a photon of wavelength of 486 nanometers. Okay, well, we know that we will need a difference of 4.09 and 4.09. So the only way to get a difference of 4.09 would be to take away this value and this value. So if we go from here to there, then we're going to get 4.09, and this is simply because the difference between minus 5.45 and minus 1.36 is equal to this number. Now, why is the arrow going down? And this is because that anytime we have an emission, our electron drops in energy level. So this is just because of energy conservation, but if we have an emission, the electron will drop in energy level because some of the energy has gone into a photon. Okay, question 6, last question of this paper. Describe the Doppler effect. Well, the Doppler effect describes the change in observed frequency when the source moves relative to the observer. Notice that because it says the word describe, I've not actually used equations. Part B, explain how ultrasound is used to measure the speed of blood flow in an artery. Well, pulses of ultrasound are reflected off of moving blood cells. The transducer is actually placed at an angle to the artery, and then the frequency of the reflected waves is different. You can actually use the equation that delta F is equal to 2FV cos theta divided by C, where C is the speed of sound in the medium, and then all you need to do is just rearrange this equation for V to get the right answer. Okay, let's have a look at part C. So in cosmology, the Doppler effect can be observed with light from distant galaxies, and the Doppler effect can also be observed with sound waves. Yep, that's absolutely correct. Now, two students use sound waves to investigate the Doppler effect. We have some open space, and essentially we have one student that is spinning this loudspeaker that is placed on a piece of string, and then we have another student with a microphone that's connected to an oscilloscope. The loudspeaker emits sounds in all directions with a single frequency of 1700 Hertz. Okay, figure 6.2 shows the variation with time t of the frequency f received by the microphone, and as we can see that the frequency will be varying like so. This will actually be quite a fun experiment to do within the laboratory. Okay, use figure 6.2 to show the speed of the loudspeaker is 7.5 meters per second. Okay, well, you can see that every time one full cycle is complete, the loudspeaker would have returned to its original location. So this means that our time period actually is just 0.5 seconds, because it's t on the x-axis. So let's use the figure to show the speed of the loudspeaker is 7.5. So our time period t is 0.5 seconds. If this thing is spinning and it performs one full cycle in 0.5, then we can just use v is equal to 2 pi r divided by t, and that will be 2 pi multiplied by the radius, which is 0.6. So 2 pi times 0.6, divide that by 0.5. And if we put that into a calculator, we're going to get about 7.54, which is about 7.5 meters per second, up to two significant figures. Okay, for the next part, what we needed to do was to calculate the change in frequency, and I've just used Doppler's effect. So delta F over F is approximately equal to V over C. I've just rearranged for delta F to give me V times the original frequency divided by C. Please pay attention that F here is the original frequency of an unmoving source, so 7.5 times 1700 divided by 330, which is given here, it's going to give us about 39 Hertz. Now let's complete the scale on the y-axis on figure 6.2. Because our change in frequency will be 39 Hertz, this means that the frequency will be changing by that amount. So our maximum perceived frequency will be 1739 Hertz, so 1700 plus 39, and our minimum perceived frequency will be 1700 take away 39. Okay, next one over here, mark with an X on figure 6.1 the position of the loudspeaker which corresponds to point X. Okay, so let's have a look at point X. So point X is minimum frequency, isn't it? So that's minimum frequency, which means maximum wavelength, which means maximum redshift. Now, if the redshift is at a maximum, this means that the object must be moving away from us at the fastest rate, and the only place, the place where this is happening, where the object is moving directly away from us, is right here. For instance, just this point here, let's call that, I don't know, I'm going to call that point Y, just to help you guys really understand this question. Where would this point be? Well, this will be the maximum perceived frequency of the sound, which would mean that the object will be going towards us, so this will be right here. Of course, this is not actually part of the answer, but I wanted to help you guys with the understanding of this question. And let's have a look at the very final one, a classic question. Define the following terms: accuracy and precision. So accuracy is how close the actual values are to the true value. So let's just say how close the measured values are to the real or to the true value. And precision involves how close the measured values are. In other words, how low of a spread they have. And that's the end of the question paper. Okay guys, well, thank you very much for watching. I'm hoping this video was useful. It was a long one. Good luck on your exams and good luck with your revision.